We tend to think of the ingredients of the universe as static building blocks, but the creation of heavy elements requires extreme, violent mechanical events to force atomic nuclei together against their own repulsive forces. The modern periodic table organizes these elements by their chemical properties. It tells us how they interact, but it completely obscures a crucial physical reality: the massive disparity in how much of each element actually exists. This chart shows the distribution of elements based on the solar surface composition, our true empirical dataset. Notice the vertical logarithmic scale. The mass difference between the abundant elements at the top left and the heaviest trailing along the bottom right is staggering, a 10 billion-fold difference. These peaks and valleys function as a physical ledger. They record the precise physical limits and mechanical regimes operating throughout the history of the universe. To read this ledger, we have to isolate its distinct data features. First, there is the overwhelming dominance of hydrogen and helium clustered at the extreme top left. Second, immediately following helium, there is a massive, sudden drop-off in abundance, followed by a jagged, uneven climb up through carbon and oxygen. Third, further down the plot, the data forms a highly prominent isolated spike occurring at iron. And finally, a long scattered tail of heavy elements trails off to the far right, categorized entirely by separate mechanical labels like the S process and R process. Decoding these distinct clusters requires reverse engineering the specific astrophysics behind each one, tracing how thermodynamic forces mandated their creation. Analyzed through this lens, the chart reveals how thermodynamics dictated the existence of our material reality. Hydrogen and helium represent roughly 98% of all mass in the Sun, and by extension, the observable universe. These elements were synthesized in the first hour of the universe, during the rapid cooling phase immediately following the Big Bang, rather than being forged in stellar cores. To build anything heavier, you need a new engine. In stellar interiors, immense gravitational pressure heats matter to millions of degrees, stripping electrons from their nuclei to create a superheated plasma. This diagram shows the proton-proton chain. 4 hydrogen nuclei convert into 1 helium nucleus, while a proton transforms into a neutron. The resulting helium has slightly less mass than the initial protons. That mass difference converts directly into extreme energy, governed by Einstein's equation. This engine sustains the star against gravitational collapse for billions of years. However, it relies entirely on primordial fuel, leaving the remainder of the chemical distribution unexplained. Look at the data immediately following helium. Abundances plunge precipitously. This gap exists because of a strict structural limit. There are no stable nuclei with atomic masses of 5 or 8. Adding 1 proton at a time to build a heavier element becomes mechanically impossible past helium. To bridge this gap, the universe uses the triple alpha bypass. Deep inside giant stars, 3 helium nuclei merge simultaneously. They manage this through a specific resonant energy level, forging carbon-12. Once established, it rapidly captures another alpha particle, forming oxygen-16. This comparison compares the solar chemical distribution with the Earth's crust and the human body. While the Sun is overwhelmingly hydrogen and helium, human biology is dominated by oxygen and carbon. The existence of complex biology on our planet depends entirely on stellar cores successfully executing that specific thermodynamic maneuver to bridge the mass 5 and 8 gap. Returning to the dataset, we see a jagged upward trend immediately following oxygen. In stars at least 10 times more massive than our Sun, central temperatures climb so high they trigger a runaway sequence of these alpha captures. The core systematically fuses heavier species: neon, magnesium, silicon, sulfur, argon, calcium. But this rapid ascent up the fusion ladder terminates abruptly. The entire sequence crashes into the massive abundance spike at iron 56, which marks the absolute mechanical limit of the stellar fusion engine. This prominent iron peak signals that the star has reached a final, insurmountable thermodynamic barrier. The lifespan and capabilities of a star are governed by the binding energy per nucleon. This graph displays how elements achieve nuclear stability. Starting from hydrogen on the left, fusion processes seek a more stable, lower energy state. Follow the downward slope. The curve bottoms out exactly at iron, which possesses an exceptionally high binding energy per nucleon. This creates a thermodynamic wall. Synthesizing elements heavier than iron through fusion is an endoenergetic process. It consumes the star's energy instead of releasing it. Furthermore, electrostatic repulsion, the Coulomb barrier, increases with the number of protons. The resistance between highly charged heavy nuclei becomes too strong for the core's heat and pressure to overcome. Standard stellar fusion is mechanically incapable of building the heavier half of the periodic table once it hits the thermodynamic dead end of iron. If core fusion permanently stalls at iron, what physical mechanics produced the heavy elements trailing across the rest of the solar abundance plot? To bypass the Coulomb barrier, the universe utilizes uncharged particles. While a highly charged nucleus will violently repel an incoming proton, a neutron can easily slide past the defenses and penetrate the nucleus. Bathed in a high neutron flux, a nucleus can capture neutrons and grow heavier without fighting electrostatic resistance. Because free neutrons are unstable, they rapidly undergo beta decay, transforming into protons and stepping the atom up the periodic table. This occurs in two specific regimes. The slow neutron capture, or S process, operates over long periods in aging giant stars. This slow flux accumulates material at magic stable nuclei, creating the specific secondary peaks you see at strontium, barium, and lead. The rapid neutron capture, or R process, requires catastrophic intense fluxes, the kind generated by supernovae or binary neutron star mergers. These violent events bombard nuclei with neutrons so fast they overwhelm the standard rates of radioactive decay. Every heavy element on Earth, from the silver in your electronics to the uranium in a reactor, exists strictly because of these extreme post-fusion neutronic bypasses. This is the cosmic abundance curve. The left peak records the Big Bang's cooling. The jagged ascent maps hydrostatic stellar fusion, climbing the alpha ladder until striking the thermodynamic wall at iron. The long tails result from extreme neutron fluxes in dying stars. The chemical composition of our universe provides a direct, readable record of its entire thermodynamic history.